Class 100. I'm Professor Curtis, your instructor for this course. This is the lecture for Chapter 26, Properties of Light. Let's get started. So we've already been introduced to Sir Isaac Newton in our study of mechanics, and it was his work in mechanics that gave us what we call the first great unification in physics. In other words, he's trying to put together a series of laws and principles that together collectively describe our understanding of the physical world. Well, there was a second great unification that occurred in physics with a Scottish physicist named James Clerk Maxwell. And he lived in the late 19th century. This was a mathematician, what I call the original Victorian geek, because he liked to spend his weekends just sitting around thinking about math equations. So again, not my idea of a great weekend, but you know, I'm grateful for Mr. Maxwell, and I'm sure that when we get done with this lecture, you're going to be grateful for him as well. One of the reasons why Maxwell's equations are so fundamental to our current understanding of physics is that they demonstrate that all electromagnetic waves have an electric field component and a magnetic field component, and that the electric field and magnetic field act perpendicular to one another, as you see in the diagram here on the screen. The other reason why Maxwell's equations are so important is that they show that light is an electromagnetic wave. So everything that we know about electromagnetic waves applies not just to, microwaves, radio waves, gamma rays, X-rays. They also apply to light. And we'll see as we get into future lectures how very instrumental that's going to be. But first, let's take a look at Maxwell's equations themselves. You can see them here on the screen. 4 simple partial differential equations. Now, this is definitely math that is beyond the scope of this class, but as I've always had students who like to see the calculus portion, and partial differential equations is basically a step beyond calculus. So this is what they're looking at here, and I know this looks like, gobbledygook gibberish jash to some of you guys out there, but as I said, math is a language, and there are people that can make sense out of this. So obviously, because the math is beyond the scope of this class, you don't need to know these equations. You're not going to do anything with them. But you do need to know about them. You do need to know the concepts that come to us because of Maxwell's equations. First of all, these equations are the foundation for all modern electrical and telecommunications technologies. So that smartphone that a lot of you out there are addicted to, you don't have any of that technology without Maxwell's equations. Maxwell's equations lay the groundwork for that. These equations also tell us that light is an electromagnetic wave with electric and magnetic field components. We'll get into that in a moment. These equations also tell us that all electromagnetic waves travel at the same speed in a vacuum. And if they travel at the same speed in a vacuum, well, if we know how fast the waves are traveling, well, there's a lot that we can do with that knowledge. Let's take a look at some of the implications for Maxwell's equations. He was the first to realize that light is just an electromagnetic wave within a certain wavelength or frequency range. Remember, if the speed of a wave is known, the speed of a wave is the wavelength times the frequency. So if we have a certain range for wavelength, then that means we also have a certain range for frequency, because the two multiplied together give us velocity, which we just got done saying is set in a vacuum. It's constant in a vacuum. There's just one speed at which an EM wave can propagate in a vacuum. So this is actually part of the conservation of energy principle. Think about it for a moment, okay? The EM wave components reinforce each other. So if a wave were to slow down in the same medium, okay, in other words, if it didn't have a constant speed, but it were actually slowing down, then that would mean that the electric and magnetic field components would get smaller and smaller and smaller. And the result would be total energy loss just for existing. And so that's a violation of the conservation of energy principle. On the flip side, let's say that the EM waves speed up in the same medium. Well, then that means the electrical and magnetic field components are going to get larger and larger, and then the result will be an indefinite amount of energy gain, again, just for existing. Obviously, this is not what happens. In order for energy to be conserved, because energy cannot be created or destroyed, just transformed or transferred. So in order for energy to be conserved, the speed of the wave has to remain constant when it's going through the same medium. Maxwell's equations also give us the value for speed of light. Again, like I said, the original Victorian geek, this guy liked to, hang around on the weekend and just play with math equations in his head. And no, not my idea of a great weekend, but it gave us all the modern telecommunications technologies that we have today. So I'm thankful that he was willing to do that with his weekend, so that some of us didn't have to do the same thing, and we can enjoy the fruits of the labor. So if you take Maxwell's equations and you consider the case of an electromagnetic wave traveling in a vacuum, the equations reduce to what you see there on the screen. Now, I know to some of you that doesn't really look like it's all that much different, but we can see some different effects here from Maxwell's equations. First of all, there's no electric charge and no current in a vacuum, and that's part of what simplifies his equations. Now, I know some of you are looking at that and saying, well, how is that any more simple? Well, compare what you see here to what you saw earlier. Okay, notice for the first two equations, those get set equal to 0. And then there's some changes in the second two equations that also make for simplification. But one of the most important results of that simplification is, if you look at the last equation there, see that letter C squared down there at the bottom of that first fraction? That C represents the speed of light. And it was Maxwell who sat there and was actually playing around with numbers in his head and came up with an actual value for the speed of light, 300,000 kilometers per second. Now, he did this in his head. Now, this is another reason why I call him the original Victorian geek, because the true value that we've been able to measure today is 299,792.46 kilometers per second. So you could see, playing with numbers in his head, this guy got really, really close to the actual value. I think he's a pretty smart guy. And again, I'm glad he spent his weekends doing what he did, because, man, I wouldn't want to have to put the foundation for modern telecommunications in place. So we see from Maxwell's equations, the speed of light in a vacuum is essentially the speed at which all EM waves travel in a vacuum. Because remember, light is just another type of electromagnetic wave. So remember, we learned earlier about waveforms, the velocity of a wave is equal to its wavelength times its frequency. And since all EM waves travel at the same speed, the only difference between the different types of EM waves is their wavelength and frequency. So if an EM wave has a large wavelength, it's going to have a small frequency. And if the EM wave has a small wavelength, it's going to have a large frequency. So that's the only way you can multiply two numbers together to get the same number. If one of them gets bigger, the other one has to get smaller. If one gets smaller, the other has to get bigger in order to come out with the same number when you multiply them together. Now, all EM waves produced by an oscillating electric charge will have the same frequency as the electric charge to produce them. And since the velocity of the waveform is known, we know that it's equal to all the EM waves travel at the speed of light, then that means that we can also find the wavelength for an EM wave that's produced by an oscillating electric charge. To help us understand the different types of EM waves better, we categorize them in what's called the electromagnetic spectrum. And there's not really any hard and fast boundaries between categories. It's more like it's kind of fuzzy. It's like this part of the spectrum is for gamma rays, and this part is for X rays, and this part is for ultraviolet. The hardest boundaries you're going to find are for the visible light spectrum, and that's because it's based on biology. It's based on what human eyes can actually detect and sense. But outside of that, the different categories for the electromagnetic waveforms are pretty fuzzy. But if we look at, say, like a whole spectrum for the visible light, okay, notice it runs the gamut there from one end to the other. And so on the left end, where you've got towards the purple end of the spectrum, you've got shorter wavelengths, higher frequency, and higher energy. And on the other end, which is the red end, you've got longer wavelengths, which means you've got lower frequency and lower energy. So if you look at the difference in the waveforms, you can see there on the purple end, notice how the waveforms are crunched together. This is a shorter wavelength, which means in the same period of time, you're going to see more complete waveforms pass through a given point. That's the higher frequency. And of course, with higher frequency, you get higher energy. Over towards the red end, notice how everything gets elongated. So everything gets kind of stretched out. So you've got a longer wavelength, which means in the same amount of time, you don't see as many waveforms pass the same point. That means you have lower frequency, and with lower frequency, you get lower energy. Let's talk a little bit about conventions that we use when talking about electromagnetic waves. Each electromagnetic waveform has a wavelength that corresponds to a unique frequency because the speed is set. So we only need to use one of those variables, frequency or wavelength, to describe the different types of EM waves. Again, your textbook author tries to simplify everything, and in doing this, he uses frequency to describe everything, including visible light. But this runs counter to the convention that's been popularly adopted by the rest of the world, which is using wavelength for visible light and then frequency for everything else. This is the convention that I'm going to use in the course because it's the convention that everybody else uses. So instead of trying to simplify everything, let's just get on board with the same bandwagon that everyone else is on. And then I think when we start to talk to other people about this, it'll actually be easier to communicate because we're all using the same convention. So with that in mind, look at your workbook and find a copy of the electromagnetic spectrum there. And then keep in mind that all EM waves have the same speed. So we're going to use 300 million meters per second to make the math a little easier. A little easier. You still got a big number to play with, but hey, that's all right. And then wavelength and frequency are going to differ for the different types. So find the frequency for EM waves from the sources that you see down here below, and then identify what group they belong to in the electromagnetic spectrum. So you see here I have listed a cell phone, which has a wavelength of about 0.35 meters. We have a radio wave from a radio station, 102.5 FM, and that's going to be 2.93 meters. And then the wavelength for the waveforms coming from a wireless internet router, 0.13 meters. And then UVB radiation coming from the sun, and you can see that's a really short wavelength there. So take a minute, stop the video, and perform some calculations with this. What frequency do we have for each of these EM waveforms? And then can you categorize them based on what you see from the scale that you see up there at the top? So go ahead, stop the video, work this out, and then come back and we'll see how you did. All right, let's see how well you did with this. So first up, we have the cell phone. And the cell phone has a wavelength of 0.35 meters. So the velocity is going to be equal to the frequency times the wavelength. So if we rearrange that to solve for just the frequency, we're taking the velocity of the waveform, which is the speed of light, and we're dividing it by its wavelength. And you can see what we get out of that: 850 million hertz, or 850 megahertz. The radio wave coming from radio station 102.5 FM. Oh, I forgot, we're supposed to categorize each of those waveforms. So the cell phone would be what we call a microwave. And then, let's see, from the radio station, we've got, look at that. Look at what it comes out to be, 102.5 megahertz, that's where the numbers on your radio dial come from. They're actually giving you the frequency of the radio wave there in megahertz. And of course, that's forms to the radio wave portion of the spectrum. Wireless internet router, you can see here 2.4 gigahertz. That's a typical frequency for a wireless internet router. And of course, that puts it into the microwave category, same as your cell phone. UVB radiation, wow, there's a, what is that? Let's see, 1,000, million, billion, trillion, quadrillion, 300 quadrillion hertz, which is, using that metric system. Again, we've got 300 petahertz. That's a lot of hertz. Of course, that puts us in the ultraviolet portion of the spectrum. So you can see from the spectrum up there, if this puts you in the ultraviolet, you can just imagine the frequency for X-rays and gamma rays is even larger. And so that's kind of run through with that. But yeah, you can see the differences here from the different types of waveforms we have in the electromagnetic spectrum. Let's talk a little bit more about light. So most materials do not allow light EM waves to pass through them. And so we call these materials opaque because they block the light. They don't let the light through. But there are some materials that do let light pass through them, and these materials we call transparent. So all EM waves are carrying energy, and each energy level has a frequency associated with it. So what is it that determines whether or not the light waves can pass through the material or not? Well, it depends on the resonant frequency of the electrons in the material. Essentially, when an EM wave encounters a transparent material, the energy in the EM wave is going to cause the electrons of the atom of the surface of that material to vibrate. So it's like, the light wave hits it, and there's a transfer of energy from the light wave to the surface of the material. And that extra energy is going to cause the atoms there on the surface to vibrate. Well, every material has a certain natural vibrational frequency. And so when the EM wave energy that comes and hits those atoms on the surface, if that extra energy causes a vibrational frequency that's the same as the natural vibrational frequency for the material, then that energy is going to be accepted in the material, and it's going to transfer through the material. Because it matches the frequencies. This is an effect we call resonance. And so the energy is going to be continually passed on. Okay? So think about it like, bouncers at a club. If the energies are the same when they come up, then that means it's like, hey, you're one of us. Come on in. Join the party. Okay? And so that's how materials become transparent. So when the EM wave actually enters the material, the speed will decrease when it's passing through the material. Okay? It's still constant within the material, but it's traveling at a lower speed than it would be, say, out in the open air. Once it emerges on the other side, then the speed returns to the value that it had before it entered the material. So If the energies are like when the light wave hits, then that is going to transfer through the material. That's what makes the material transparent. If it's not, this can be like the bouncers say, hey man, you don't belong here. They'll bounce the energy out, and then because the energy doesn't transfer through, the material is what we call opaque because we can't see through it. So that's essentially what happens when we get light waves, because the resonant frequency of the material does not match the frequency of the light waves. The material, the atoms there on the surface where the light waves are hitting, they're still going to be transferring some energy there. And so the atoms that are there on the surface are still going to vibrate. But because the frequencies don't match, okay, the energy is not accepted into the material. It doesn't pass through. And so we don't see light waves passing through that material, and that's what makes them opaque. Of course, if the energy is not passed on, there's still conservation of energy going on, right? So what happens to the energy if it's not transferred through the material? Well, the vibrations of some of the electrons are going to cause them to emit their own EM waves, when that is essentially a reflection of the energy that's being put onto it. But most of the rest of the energy is converted into random kinetic energy inside the material. And of course, when you increase the kinetic energy of the vibrations of the atoms, you're going to increase the temperature, because that's what temperature is. And so that's why you leave stuff out in the sun, it gets warmer. And that pretty much brings us to the end of this video. I hope you found it helpful. Thanks for watching, and we will see you in the next video.